Hi class, today we're starting chapter 2, Exponential and Logarithmic Functions. And in the first section, we're just going to be covering a review of exponential and logarithmic functions using the e as the natural base. So we're going to graph and solve exponential functions and logarithmic functions using e as our base. Let's get started. As we go through section 2.1, you should know that all of this stuff is review, and that you should have learned exponential and logarithmic functions previously in another class. So you should have already learned about e, which is a constant, approximately equal to 2.718, and this number goes on and on and on and on. It's irrational, but this might be new to you, the limit notation. And so if you graph the graph 1 plus 1 over n to the nth power, and if you looked at the graph as that goes towards infinity, then you would see that that value, the y value of this function, will approach this value. And notice that that's not in this formula, this compound interest formula that we used in previous sections, but it is in this one where if you're compounding continuously. Now what's the difference between the formula up here and the one we have highlighted in yellow? The difference is this one is compounded n times per year. So if you have something that's in a bank account that's compounding quarterly, that's going to compound 4 times per year, n will equal 4, and then we would replace that value with 4 and we would plug it into this. Versus something that's compounding continuously, something that's growing exponentially, you're just going to use e to the power of rt. And so we're going to see the differences between this first formula, which we used before, and the second one, which we're going to be using today. This is example 1, and this one will be example 2. For our first and second example, we have the same situation. Rachel will be investing $20,000 into an account that earns interest at an annual rate of 4%. What we're going to do is find the value of Rachel's account after 3 years if interest is compounded at different times. So for the first one, it says compounded annually, then semi-annually, then weekly, and then we will also see if it's what happens when it gets compounded continuously. For this question, the rate is 4% and the time will be 3 years and the principal is the $20,000. But what's going to be different in each question is the n. So when something is compounded annually, that's 1 time a year, so our n will be 1. So plugging that n value into our formula, we can simplify this a little bit before plugging into our calculator. Okay, and so make sure that you take 1.04 to the third power first and then multiply by 20,000. Or use your graphing calculator, it will know which order to do the steps. So using my calculator, I got $22,497.28. Make sure that you always put the correct units on it. And make sure that you always take it to a place value that makes sense. Either round it to dollars or round it to cents, but don't round it just to 1 decimal place or to 3. That's a little awkward when we're dealing with money. So we want to make sure we do it to either a full integer or to the hundredths place. Notice semi-annually says n equals 2 for us already, so let's write that into our formula. And then simplify it once. So this is 1.02 to the 6th power because we had to take the 4%, divide it by 2 to be able to do it twice each year. Now we got $22,523.24839, which we want to rewrite. So we're going to round it to the nearest penny. And since the 8 is an 8, we're going to round up. So we get $22,523.25. Notice that this is more than our original answer when it only compounded once each year. And now we're going to get a little bit more money because we compounded twice. Let's keep on going. If we want to compound weekly, we have to think about how many weeks are in a year. And there are 52 weeks in our year, so our n is 52. Let's write that into the formula. And 52 is such a large number that this is going to be hard to simplify. So just make sure that when you type it into your calculator, you type it okay. And you might need to put parentheses around the exponent because this is 52 times 3. So you need to make sure all of that's there. When I input it into my calculator, I got $22,548.89682. Now let's write that properly. We'd have to take that 9, round it up because of the 6, but not write 9. We need to write 90 for 90 cents. And then let's just compare that to the previous answers. Notice that every time you compound more often, you end up with more money. So notice that increase. Video example 2 has the same setup as video example 1. We still have Rachel investing $20,000 into an account, but the difference is that it's not compounded annually, semi-annually, or weekly. It will be compounded continuously. And so then we have to use a different formula. We're going to use E instead of the R over N. And so let's see what happens when we plug that E in. So let's go ahead and write it out. And you can just let your calculator solve it for you. Make sure that you use parentheses if necessary. I get $22,549.93703. We'll round that to 94 cents. Just compare it to all the other answers we have. And so that is where you get the most money if you compound continuously. So we've done a question that had the E as the base of the exponent. And now we're talking about logarithms. And when you use the E as the base of the logarithm, we call it the natural log. And we write it as ln for natural log. Well, log natural because that's in French. But we don't write it as log base E, we write it as ln. And then don't forget that y is equal to ln of x is equivalent to writing e to the y is equal to x. So if we have a statement that's like e to the k power is equal to 5, and we want to take the k out of the power, we want to rewrite this equation, then we would write it in this manner, and I would pull the y out, or in this term I would pull the k out. The exponent becomes the part that comes out. We'd say log base e, or ln of 5. And so these two statements would have equivalent values for k. And I just want to review some properties of natural log. If we have multiplication inside our argument, then that can turn into addition of separate logs. If we have division inside our argument, that turns into subtraction of separate logs. And if we have the natural log of something to a power, you can take that power and make it a coefficient and then say natural log of m. Now natural log of e will always be 1. Natural log of 1 will always be 0. And then here we have the change of base formula. Or if we have log of any base of m, then that can turn into natural log of m divided by natural log of b. And if you have natural log of m, you can turn that into log of m and log of e, where the log of any other base. Natural log of e to the x is x for all real numbers x, and e to the power of natural log of x will also be x. That's because these are compositions of inverse functions, and so the natural log and the e to the x are inverse functions, and when you compose them like this, or you compose them like that, then they cancel each other out, and we end up with x as our solution. We're going to use these properties of natural log to simplify each of these statements. And so for the first one, we're going to use the third rule, pulling down that exponent. And then we're going to use the fourth rule, where ln of e is just equal to 1. So we just end up with 4 as our answer. For ln of 1, the fifth rule says that ln of 1 is always 0. So that's done. For part C, we're going to do it similar to part A. We're just going to bring down that exponent, and then we're going to write it as that going to 1, so we don't have to write it anymore, so we've simplified it to be -1. Now ln of 20, that's more difficult. Let's use our calculator to do that because we can't simplify this any other way. And so the calculator says 2.99573, and the question says to approximate values to 3 decimal places. So we're going to write 2.996. Alright, there we go. For video example 4, we were given 2 natural log values. That is, we're given ln of 2 and ln of 5. And then it says to use the properties of natural logarithms to find each of the following. Notice that each of the following involves numbers that are multiples or factors of 2 and 5. And so if we could take these numbers and rewrite them in terms of 2 and 5 using the rules of logarithms, then we can evaluate these. So the first one is ln of 10. That's ln of 2 times 5. And multiplication inside the logarithm turns to addition of 2 separate logarithms. And so all I have to do is substitute these values in. And using my calculator, I got 2.3025. The next question, ln of 8, that's ln of 2 to the 3rd power. And we can take that power and bring it down to be the coefficient. Now it's just 3 times ln of 2. So plugging in that value of ln of 2, which is 0.6931, we can just use our calculator to evaluate this. Alright, and then ln of 5 over 2, that is division within the natural log, which turns into subtraction outside the logs of 2 separate logs. And then we can just substitute these. And then ask our calculator, and we get 0.9163. Let's continue on to parts D and E. We want to separate out all the terms. So it'll be ln of 5 plus ln of e squared, which will just be ln of 5 plus 2 ln of e. Replacing ln of 5 with 1.6094, and then replacing ln of e with 1, we just end up with 3.6094. And then log base 5 of 2 can be written as ln of 2 divided by ln of 5. Once again, all of these rules were just reviewed. So if you don't know where I'm getting this from, look at those rules. This would be 0.6931 divided by 1.6094. And I get 0.430657. And as a general rule of thumb, you want your answer to match the question. So since we were given 4 decimal places as part of the question, we want our answer to be to 4 decimal places. So we're going to round it to this place value, and we're going to round up. When we're talking about natural log, it only exists for positive numbers, and so when you graph it, you only graph values which are greater than 0 all the way to infinity. That's the domain, from 0 to infinity, but not including 0, not including infinity. Notice that natural log is less than 0, meaning that the y values are negative for values between 0 and 1. And then we also have the natural log is positive, or it's greater than 0, for x values of greater than 1. And then natural log of x is 0 at x equals 1. Notice that natural log right here is equal to 0 at x equals 1. It's an always increasing function. The range goes from negative infinity to positive infinity, but the domain is only positive numbers, so greater than 0 all the way to infinity. Let's practice finding the domain of these 2 natural log functions. Remember that the rule for the domain of logarithmic functions is that the argument must be positive. And the algebraic way to write must be positive is greater than 0. So we'll write the argument 4 minus 5x has to be greater than 0. Let's solve this. And then we'll divide by a negative number. And that makes this sign turn around. Writing this in interval notation, we would have from negative infinity to positive 4/5. Let's do it again. So once again, the rule is that the argument must be positive. We would take the argument, 3x minus 7, and state that it has to be greater than 0. Adding 7 to both sides, and dividing by 3, we end up with the interval from 7/3 to positive infinity. Remember, the sign only changes direction when we divide by a negative, but when we divided by a positive 3, we kept the sign going that direction. That changes which side of the interval that your number will be sitting on. For question number 6, we're asked to solve the following exponential equations using logarithms. And so we want to take this equation and rewrite it as a logarithmic equation. Notice that the exponent should be pulled out, and then we should call it log base e, or ln, of 80. It's that simple. And then we need to use a calculator to give our answer to 3 decimal places. So there you go. There's t. We're going to do the same thing here. We're going to say pull out that exponent and then divide by that coefficient. So using your calculator, I got 17.3286, so we will write 329. Remember that you have to round appropriately, so even though it said 328, we're writing 9 because we rounded up. Before we can rewrite this last one, we do want to divide by the 67 to isolate our exponential function. And just leave it in exact form because that won't divide evenly. And then we can take the power and rewrite it as 0.45t is equal to natural log of 500 over 67. And then we're going to divide by the 0.45. You also can write this as ln of 500 minus ln of 67. You don't have to. I just want to make sure you know your options. And if you see that answer and you want to know where it comes from, it's because we can take the division, turn it into subtraction. And then let's use our calculator to help us solve this. So it says 4.4664, so we don't need to round up. And there's our solution. We have a theorem about the exponential growth rate, and that's expressed by r as a decimal, and the t for how much time it takes. So when you do r times t, if you want to know how long it takes to double, then you would put ln of 2. And so r times t is equal to ln of 2. That means that if you know the rate, you can say, oh, I have something that is earning 10% interest. Then you would take ln of 2 and you divide by your rate, and then that gives you how much time it will take you to double your money. Now the 2 here is important that you know that it's related to the fact that we're using doubling time. If we want to know how long it takes to triple our money, we'd replace that with a 3. If we want to know how long it takes us to quadruple our money, we would replace that with ln of 4. And so the fact that we're looking for doubling time is why we're getting ln of 2. We're revisiting the same scenario we started off with. Rachel investing $20,000 into an account that earns 4% annual interest compounded continuously. When will her account be worth 3 times her initial deposit? Now, let's go ahead and solve this as if we don't know the rule that we just put on the board. If we're starting off with $20,000, how much will it be when we get 3 times her initial deposit? That would be $60,000. So we would say $60,000 is the amount we want to have. We want to start off with $20,000, and that's E times the rate of 0.04t. How do we solve for t? First, we want to isolate, so we're going to divide both sides by 20,000, and we're left with 3 equals to e to the power of 0.04t. And then we're going to pull down that power and make it natural log of 3. So see where that natural log of 3 comes from? And then we're going to divide by that coefficient. So notice that 3 comes from tripling our initial deposit, 0.04 comes from our rate, and then we would just ask our calculator. And it will take you approximately 27 years to double your money. But instead of starting over here, we could just say, you know the formula. Let's just start at this step. Let's just replace this value with what we want to do. Do we want it to be doubled? Do we want it to be 3 times our initial deposit? And then this is our rate, and then we can solve for time. That saves us some of the steps of algebraic work. For video example 8, the question says, revenue from sales of digital content by the New York Times doubled over the 6-year period between 2011 and 2017. Assuming exponential growth of the digital revenue during this period, what was the exponential growth rate? Now for this question, we know how much time it took to double, but we don't know the growth rate. So we're actually going to be solving for rate instead. Notice we know the time, so we're going to use that in a formula. We're going to be solving for rate. I'm using 2 because that's what it says, it doubled. Let's go ahead and plug this in. So if I replace t with 6, since it took 6 years to double, then I can solve for r. And my calculator tells me that that is 0.1155. In other words, that's an 11.55% growth rate. For video example 9, I have a logarithmic equation and I have a variable inside the logarithm and I want to solve for that variable. So the first thing I'm going to do is try to isolate the logarithm so that I can rewrite this as an exponential so I can pull the argument out of the logarithm. In order to isolate the logarithm, the first thing I'm going to do is subtract 5 from both sides. And then I'm going to divide by the coefficient of 7. And then notice that now I have my logarithm isolated. I can pull out that argument of the logarithm and see it's equal to e to that power. And then I want to isolate the variable. So I get x is equal to e squared minus 3. And many times we refer this as our exact answer. But if you're asked to have a decimal approximation, you could use your calculator and you could say 4.389. So once again, here's my exact and here's my decimal approximation. All right, so we reviewed a lot of properties and a lot of rules here in this section, and you should go and do your homework and take time to remember all of those rules. Thank you and have a good day.